Okay, I think let's get started. So, any question from this time? Yeah, so this time we start doing this optimality of Grover's algorithm. So basically, we are trying to show that to solve this search problem. So I should go to the search problem. Okay, so we have the search problem, and which gives this oracle as input. So we have this small x as input, and want to distinguish whether f of x has a mark item or. So that's a yes case. Yes case f of x is a mark item. Sorry, I swap those yes and no now. Okay. So yes case f of x is a mark item, and no case f of x has no mark item. And yeah, so we want to search over these input, these values of f of x and see whether any one of them is marked. And we are showing today, so you can do this with Grover's algorithm. And we are showing today that in fact distinguishing, so we can do this by Grover's algorithm using square root and oracle codes as we have shown before. And now we are trying to show that indeed we also need omega square root and oracle codes to solve this problem using any algorithm. Okay, so that means that Grover's algorithm is optimal. And the way we show this is we are tracking this progress measure. That is the summation of distance between pairs of states. So those states are what are the state of your algorithm. Okay, so the state psi kx and sorry psi xk and psi k. They are the state of algorithm when your oracle is has no mark item, or your oracle has mark item on x on x. Okay, where okay, so try to differentiating whether there is no mark item or there is a mark item at the location x. And then we want to sum over all x to make sure that our algorithm can distinguish each one of the pairs. So the algorithm should be able to distinguish no input or one input at any location. Okay. And so we check this progress function. That's the state of your, once again, that's the state of your algorithm after case oracle call. And and between whether the input is whether the oracle has mark item x or the oracle has no mark item. Okay. And we check this progress function, and we are able to show that the progress function cannot grow two-phase with respect to number of oracle calls. So we show that if you use only k oracle calls, then the progress function can only grow as order k squared. And then also argue that at the end of the algorithm, so t is the total number of query using algorithm, and we show that at the end of the algorithm, the distance must be large for so this progressive function must be large for your algorithm to be able to distinguish between any pair of input to be correct on any for your algorithm to have the correct output on any input. So when there is no mark item, the oracle should be able to say no, and when there is a mark item somewhere, the algorithm should be able to say yes. Okay? And we go through this more mathematical part where we use induction to show that decay is indeed OK squared. So basically we trigger how each oracle call can change this big D. And and when there is no oracle call, the big D cannot increase. And when there is oracle call, we use the induction to show that the relationship between dk plus 1 and dk is like this, and by induction we show that dk is less or equal to dk less or equal to 4k squared. So this is order k squared. Okay, and then we have this lower bound which we argue is true last time, but today we are going to show this in detail, and we are actually trying to prove this in 3 different ways to give you a bit of hint of quantum information. Okay. And so let's start with this lower bound for such problem, or the lower bound for the the lower bound for the progress function and the end of the algorithm. Okay, and the idea is this. So at the end of the algorithm, you are going to do some two-outcome measurement to distinguish whether you have a yes input or no input. And so we have a very general thing, and before discussing the measurement, so we first realize there is a very general thing at the end of algorithm. So we want to do a two-outcome measurement at the end to distinguishing whether your input is a no case or a yes case. Okay, and anyway, you have a two-outcome measurement, and that can be a generalized measurement. But then you realize that at chapter 1 we talk about there's the equivalence between generalized measurement and the projective measurement. Okay, we say that any generalized measurement you can done with projective measurement with NCLA. Okay, so at the end of the algorithm, the generalized measurement you do, the two-outcome measurement we do, we can assume that it is done with projective measurement, and we express the projective measurement with this pair of operator P and y minus P. Okay, and so this is kind of funny notation. We use generalized measurement notation to describe our projective measurement. Okay, so you have the first measurement operator P and the second measurement operator y minus P. Okay, so you can always add some ancilla and turn your add some ancilla to your algorithm and turn the two-outcome measurement in the end as projective measurement. Okay, so the measurement is described by some projector P, and then back to trying to solve our oracle problem. And in the end of the algorithm, there should be some two-outcome measurement, and now this two-outcome measurement is described by this projector P. So this two-outcome measurement should distinguish no input or yes input, and with some constant probability. Okay, and here we put the constant probability a bit higher to make our proof a little easier. Okay, so let's say the constant probability is pretty high. The success probability of algorithm is A over 9, and that means that the failure probability is less than 1 over 9. Okay, and so what's the failure probability? Failure probability is that okay, and so there are two. I write this in a different way. Okay, so success probability is A over 9, and that means that if you have a yes input, it should be accepted with probability at least A over 9. And then you have a no input, so yes input you have a mark item, and then you have a no input, and no input you have no mark item, then your projector should accept it with probability less than 1 over 9. Okay, and in this case, then we can show that any two states that satisfy those two for some projector, these two equations for some projector, then those two states must be pretty far away. So we kind of abstract this a little bit and then write down this case. So if we have a projector P, I should say projector. If there is this projector P such that one state, so if there is a projector P, if there is a one state that accepted by the projector by pretty small probability and another state accepted by projector by pretty high probability, whereby accepted by projector, I mean this equation. So you project it with this projector and see how much the known square remain. Okay, so if you project it by the projector, if we accept it, one state is accepted with pretty low probability and with probability less than 1/9, and another is accepted with probability greater than A/9, then the state must be pretty far away. So the distance square must be greater or equal to 2/3. Okay, and let's see how this goes. And so the thing we actually want to bound, I guess the more natural thing to bound is this inner product between the two states. Okay, so we are trying to say that we want to say the distance between two states is pretty big, and then that means that the inner product is pretty small. So we are trying to get the upper bound on the inner product. So upper bound between inner product of A and B is okay. And now we want to get the projector in, so we say the inner product between A and B is you can insert identity in the middle, and the identity is so it's A and B sandwiching this 1 minus P plus P. Okay, so this is just writing identity as 1 minus P and P. Okay. And then we can use triangle inequality to say this sandwiching is less than or equal to A and B sandwich 1 minus P and A and B sandwich P. Okay. This is triangle inequality on absolute value. If there is no absolute value, then those two sides, then the left hand side and the right hand side are the same. And you add absolute value, and there are two terms, so by triangle inequality, this is greater. Okay, greater or equal to. And and then we use this known property. So the norm of inner product of two things is less or equal to. I guess this is usually Cauchy trust. So we use identity on inner product. Okay, so we say this sandwiching A and 1 minus P and B can be thinking about inner product between the vector A and the vector 1 minus P and B. And this side we say is between vector A on P and vector B. Okay, and so then by Cauchy trust, this norm of inner product is less or equal to norm of individual vector multiplying each other, product of the norm of individual vectors. So it's less or equal to norm of A and the norm of 1 minus PB. And then this part is less than or equal to norm of PA and the norm of B. Okay, and then we try to upper bound on okay, and then now we try to and now norm of A and the norm of B, because they are normalized vectors, so they should be just 1. And so now we try to upper bound the norm of 1 minus PB and the norm of PA. Okay, and here we have a bit of a long derivation, but basically what we want to say is say this term 1 minus norm of 1 minus PB. This thing square should be less than or equal to 1/9, because we say PB this norm PB square is greater or equal to A/9. And so you think about this in terms of a two outcome measurement. This is a probability of you put B inside this two outcome measurement and you get a result associated with P. And then this thing is so maybe I write it here. Okay, you think about this is representing the this two term is you are measuring B with the two outcome measurement P 1 minus P. Okay, P and I minus P, and and we say the probability, we said before that the probability of getting this thing is greater or equal to A/9, and then this is the probability of getting this thing, it should be less than or equal to 1/9. Okay, And yeah, then you just take a square root, and then you see that the woman's PB is less than 1/3. And similarly, you have this PA is, okay, so maybe I write it here, PA, okay. And also you measure A in those two outcome measurement. And then we said before that the probability of A getting P is less than 1/9. Oh, so this one don't need to prove, okay? And this one is immediate, so this one we just say PA squared is less than 1/9, and yeah, and so PA is less than 1/3. Okay, and so we see that both of those two terms are less than 1/3, and then this term is 1, this term is 1, so the whole thing together is less than 2/3. So norm of A inner product with B is less than 2/3. Okay, and yeah, so we get the upper bound on the inner product, and we can get the lower bound on the difference between those two vectors. Okay, okay, so I guess this is kind of geometric. So we say there is the upper down. Yeah. I guess, I guess let's just do with algebra. Okay, and so now we have the upper bound on the norm of the inner product, then we can turn into the lower bound on the distance. So we have, so we just basically write down this difference square, and then we expand all the terms. It should be A squared, norm A squared, norm B squared, and minus A inner product with B minus B inner product with A. And then then this is minus 2 this is minus 2 on the real part of so I guess here I actually got a little okay, here I guess we actually have a bit of typo, so this is minus 2 on the real part of AB, 2 on real part of A inner product with B, and real part, let's see. Then I guess we need to do, I think this is still correct. Okay, and I think it's easy to see that yeah, okay. And so here we use something a little more. Okay, so I guess this is technically not wrong. I need one more step. And you can always see like, yeah, okay. Yeah, sorry for confusion. And for any complex number, real part of it should be less or equal to its absolute value, right? Because absolute value is, say you have A plus BI, then the absolute value is square root A squared plus B squared, and this is also greater or equal to A. Okay, and yeah, so this is real part of AB, and it's less or equal to the absolute value, and so let's get to this equation here a bit extra step. So it's greater or equal to 2 minus 2 real part of AB, and because the real part of AB is real, and it's less or equal to this it's less or equal to this absolute value, and then this thing should be so if you are subtracting something smaller, then it should be bigger than subtracting something larger. So this something larger is absolute value of A and B, and then this is greater or equal to 2 minus 2 times where the thing we put upper bound here, 2 times 2 times 2 minus 2 times 2/3, and you do the arithmetic, and you see that it is 2/3. And yeah, so this is our bound. And then we put A and B back to what we think they should be. A is psi t and B is psi xt. Then we see that the distance squared between psi xt and psi t should all be greater or equal to 2/3 for all x. And so you just sum. So your progressive function is your sum over x is distance non-squared, and it's just 2/3 times n, and that means that at the end, the distance between the progressive function should be omega bigger. And yeah, and combined with the upper bound on how much progress you can get on each step, you see that you need at least a square root n step to give algorithm that distinguishes between all pairs of psi x and psi. Okay, and so any question? That should finish the, yeah, then this finishes the proof of our lower bound on the search problem. Quantum query lower bound the quantum query complexity of the search problem. Okay. And yeah, and this is kind of the easier way to do this lower bound. And now we want to go into a bit of information theory, and then we want to ask, okay, so we have this projector distinguishing two states, and if we have a projector distinguishing two states, then how far away can two states? Then if we have a projector distinguishing two states, then how far away the two states must be. Okay, this is kind of a quantum information theory that's very generic, and we want to kind of get a better bound on this and get it more tight. Okay, so let's formulate this. So suppose we have two quantum states, and we have a projective measurement P and a moments P, and it distinguishing those two states pretty nicely. Okay, sorry, a small typo here. And so these two outcome projective measurement distinguish those two states pretty nicely, such that if you put the state A into those two outcome measurement, then the survey probability is less than epsilon, and you put state B inside, then the state probability is greater equal to 1 minus some epsilon, suppose some epsilon. And we found out that if we have this thing, then we can have an upper bound on their inner product between A and B. That means the two states must be pretty far away from each other. Okay, so the upper bound on the inner product will be so we have a tight bound here is actually 2 square root epsilon times 1 minus epsilon. Okay. And so this is a better upper bound than we had before. If we go by this previous proof here and change this 1/9 to epsilon, then you see that the upper bound we get here is actually 2 square root epsilon. Okay, and yeah, so we get the extra 1 minus epsilon factor, which is less than 1, so we are getting a better and a tight bound here. Okay. And how to get this bound, first we do this in algebraic way, and basically we just do the algebra better. Okay, and so the first step is very similar. We break this A inner product with B into so before we have this A inner product with B into A inner product B, and sandwiching 1 minus P and P inside. Okay. And so here we just do things a bit smarter. So we have 1 minus P and P, but we also notice that 1 minus P and P are both projector. So P equal to P squared, and 1 minus P will equal to minus P squared. So instead of sandwiching P and 1 minus P, we can sandwich P squared and 1 minus P squared. Okay, and then the next step, when we break into norms, then we have more projector to attach on things. Okay, so then this Cauchy-Schwarz, we have inner product between AP and PB, and the inner product between A1 minus P and 1 minus PB. Okay, so inner product with those things, and so norm of the inner product is less than the product of the length of the individual vector. So length of PA and length of PB, and length of 1 minus PA, length of 1 minus PB. Okay. And the next step we use Cauchy-Schwarz again. Okay, and this is a bit funnier Cauchy-Schwarz. And so we use, so remember Coach Ross said sin x ax bx is equal to sin x ax squared sin x bx squared. And so basically we are saying, so this is a bit funny, so we need to sin ax bx, so this thing is, so we are saying this PA, okay, excuse me. So this PA here, this is very annoying. This PA here is A1. Oh, so maybe I just use this. Okay, so we have A1, B1, and so we have A1, B1, and A2, B2 here. Okay, so we think PA. So this is A1, B1, and A2, B2. So this is less than or equal to square root A1 squared plus A2 squared, and then this is B1 squared plus B2 squared. Okay, this is, let me see if I can write here. So this is A2, and let's see if this, okay, this is A1. Give up. It's weird. Okay. And yeah, so PA is A1, and this is A2, and this is B1, and this is B2. And so go by Cauchy-Schwarz, this is square root A1 squared, A2 squared, and B1 squared, B2 squared. Okay, so we have this thing, and we have this specific form, so that we can do things nicely. I guess the high level idea is, so those are the small terms, and those are the big terms. Because we know PA is less than epsilon squared, and from here we also have 1 minus PB. Oh, so here we should actually have a square. 1 should BB non-square should less than or equal to epsilon. Okay, so those are the two terms that should be less than epsilon, and those are the two terms that should be greater or equal to 1 minus epsilon. Okay. And so how should this term be bounded? Then so you think about this is about epsilon, this is about epsilon, this should be 1 minus epsilon, 1 minus epsilon, then together they should be less than or equal to 2 square root epsilon times 1 minus epsilon. Okay, and but we do this a little more careful because they are less or equal to epsilon, they are not necessarily equal to epsilon. Okay, so let's say those two terms sum together equal to x, and then the other two terms should be equal to 2 minus x, because this term plus this term should equal to 1, and this term plus this term should equal to 1. Okay, so this is x, and this is 2 minus x. And then we have upper bound on our inner product. So our upper bound on your inner product is x times square root x times 2 minus x. Okay, and now just think about this x times 2 minus x function. It's a quadratic function. It's minus x plus 2x, and so you plot it. Then you look at this. It's a quadratic function with roots at 0 and 2, and maximum at 1. Okay. And then when you plot it, you see it's an increasing function between 0 and 1. And that's nice for us because we know that x is less than 2 epsilon. Okay. Then the epsilon is okay, because we know x is less than 2 epsilon, so we think about some 2 epsilon here. Then this function, because it is increasing, so because we know, so I should write a little more, less than or equal to 1. Okay, because our x is less than 2 epsilon, and like I said before, we didn't quite say, but we want our epsilon to be less than or equal to 1 over 2, because the maximum amount of error is you get 1 over 2, you are just random guessing. Okay. Okay. We also assume epsilon is less than or equal to 1 over 2, otherwise the success and the failure kind of switch between each other. Okay. And so epsilon is less than or equal to 1 over 2, and so your x is less than 2 epsilon is less than or equal to 1. Then this is an increasing function, and so you see that this is square root of x minus 2x, so you have 2 epsilon here, and you know your x is less than 2 epsilon. So your x is somewhere here. And anyway, so you see that this square root of x times 2 minus x should be less than or equal to when you put x just at 2 epsilon. So it's less than or equal to square root of epsilon times 2 minus 2 epsilon. And so this thing is, as we say, is upper bounded by 2 square root of epsilon 1 minus times 1 minus epsilon. Any question? Yeah. And so this is a better bound on the inner product, and then by this upper bound inner product, then you can get another better lower bound on the distance between two vectors. Okay, so it goes through the same thing, so it should be 2 minus 2, then is square root of epsilon 1 minus epsilon. Okay, so this is the first algebraic bound, and this is tight, as we will kind of see in the next example, next way. Okay, then the next way is not quite a rigorous proof, so I guess I should put a quotation mark. So the second proof is a bit of hand wavy, but it gives us a bit of intuition of a bit of a geometric intuition of our distinguishing two state. Okay, and so basically what we are thinking is we have a two state and B we want to distinguish. Okay, and it's two vectors, and we can think about we can actually just think about the plane spanned by those two vectors and the B. And then we think about how to distinguish those two states on this plane. Then basically we want to do orthogonal measurement. Orthogonal measurement, and so we will do some orthogonal measurement with some measurement basis 0 and 1. Okay, and when you think about what's the best way to place 0, 0 and 1 to distinguish A and B, then you think then you will realize that you want this 0, 1 placement with respect and B to be pretty symmetric. And the best way to place your 0 and 1 with respect to A and B is like this. So assume your A and B have some angle here, and you want to place 0 and 1 such that 0 is closer to B like this. It has some angle to B, some angle delta to B, and 1 has the same angle delta to A. Okay. So so this is not quite proof because the first line is kind of hand wavy, but it gives you this geometric view such that you want you have two A and B with some angle, and you want to distinguish them. Then you want to have your two bases of your measurement as this 0 and 1 placed this way. You have this symmetric angle between B and 0 and A and 1. And so we want to use this A and B 0 and 1 measurement to distinguish A and B such that when you measure the 0 outcome, you think your state is B because B was closer to 0. And then when you measure 1 outcome, you think your state is A because A was closer to 1 angle. Okay. And then you think out this way, then you can calculate error. So what's the error in this measurement scheme is that say you have a B state, then you get a 1 outcome. Or you have the A state, then you get a 0 outcome. And the probability you can see just from geometry here. The probability of getting this error is B state getting 1 outcome. So it's this projection of B on 1. Then this is by simple geometry, trigonometry. This is sine squared delta. So this is this no. And similarly, the projection of your A vector on the 0 vector, then is sine squared delta. Okay, so error will be sine squared delta, and by our I guess this is actually a proof, but anyway, so there is this way to distinguish A and B. I guess we didn't prove that is the best way, but anyway, one way to distinguish A and B is doing this. Okay. And anyway, then we will see that sine squared delta is less than epsilon because how do we say? We say I guess. Sorry, I guess the statement is a bit weird. Okay, because here, so here we actually this proof. Okay, so I guess we need to put a quotation mark back. Okay. So proof one actually proves something stronger. So this is really subtle. Sorry for going into very detail. Okay, so proof one actually proves something stronger. Proof one says that if there is any measurement p, so proof one says that you just have any projective measurement p doing this distinction, then your A and B, then your A and B are pretty far away. You have a low inner product. So this is any p. Okay. Okay. And then then proof two. We actually prove something something weaker. So here we say if exists a projector P, exists P. So we have the base P that distinguishes A and B with the probability less than epsilon. With the distinction probability this area less than epsilon, then the states are pretty far away. And yeah, so this is actually prove something weaker. But anyway, this is still pretty fun to see how we can distinguish two quantum states. Okay, and so we have A and B, and we say there exists P such that so if we use the base range distinction, and so the distinction probability is sine squared delta, and if we think for this P, the probability of distinction is less than epsilon, and then we can upper bound the inner product between A and B. So now we do everything by geometry. So inner product between A and B is cosine cosine of this angle, and this angle is, well, it's very easy. There's 90 degree pi over 2 minus 1 delta here, 2 delta here. So it's pi over 2 minus 2 delta. Okay. And then we just do a bit of trigonometry, and so cosine pi over 2 minus delta equal to pi over 2 minus 2 delta just equal to sine 2 delta. And then we use the formula sine 2 delta, then it's 2 sine delta cosine delta. And then we just say norm of sine delta is square root of sine squared delta, and norm of cosine delta is the square root of 1 minus sine squared delta. Yeah, so we just use it's a square root of cosine squared delta, and the cosine squared delta is 1 minus sine squared delta. Okay. And here we do basically the similar thing, and so now we see sine squared delta is less than epsilon, and 1 minus sine squared delta is equal to 1 minus sine squared delta, and so this is basically epsilon times 1 minus epsilon, and you can do a similar analysis as this. So yeah, basically just same thing, but instead of x we have 2x here. Okay. And so you see this thing is less or equal to square root epsilon times 1 minus epsilon. Okay. Yeah, so in this proof 2 we prove something a bit weaker. We say if there exists a P that distinguishing A and B, I guess not exists P. It should be, sorry, let me think a little. This is if so we say the best way is this. So we say if so before is exists any P. So here is actually for all P. if for OP the distribution probability is less than epsilon, then they must be pretty far away. Okay. And yeah, so this is for OP, and this is just let's use more standard notation. If there exists P such that distribution pretty good. Wait, I'm confusing myself. Okay, I guess let me think about this later. Okay, and then yeah, let's go to the third way about this. This tells us even more about quantum information theory. Okay, and yeah, so this one is a bit cheating, but because we are basically using concept that we haven't talked about class, but it's in the book. Is in chapter 9 where we talk a little bit more about information theory. Okay, and yeah, but I guess this is a big way for us to introduce you a little bit about chapter 9. Okay, and so in chapter 9 there are these two concepts called transience and fidelity that let us characterize the distance between two quantum states. Okay, and yeah, so. So there are these two concepts, transience and fidelity that excuse me that both characterize as the distance between two quantum states. And yeah, as we see here, there are a lot of things that related to the distance between two quantum states. For example, what's the best probability you can get to distinguish your two quantum states? Okay, and yeah, so exactly the transience exactly characterizes its probability. Okay, so transience you can show that so it has a very algebraic. The transience has a very algebraic notation that, algebraic definition that we will not go over here, but it has a very operational meaning. That is, transience is upper bound on how much what's the best probability you can get between distinguishing those two quantum states. Okay, and so this is a gap between the measurement probability between distinguishing those quantum states. And the probability should be, as we have here, the distinction probability should be this gap, that's epsilon, and the difference between them is epsilon and 1 minus epsilon. Okay, and so transience will be the upper bound between this gap, and so it's the transience is lower bounded by the gap between those two probability. So it is 1 minus epsilon, and it's 2 minus 2 epsilon. Okay, and also fidelity. Okay, and fidelity is exactly the thing we want to bound. Okay, so for pure state, okay, so when we talk distance measure, so it was transience and fidelity can actually be defined on mixed states. Okay, but for now we have both A and B are pure state, and for pure state, the fidelity is actually just the inner product between them. Okay, so fidelity is the norm of inner product between those two states. And then there's a very interesting fact between pure state is that if your two states are pure, then fidelity squared plus transience squared will equal to 1. Okay. And yeah, so you can basically get the thing we want to bound immediately from those three facts. So you have that your inner product, absolute value of inner product is the fidelity, and equal to square root of 1 minus transience squared, just from the factor 3. And then we have a lower bound on the transience that will turn into upper bound on this 1 minus transience, 1 minus transience squared. And so it's this upper bound of 1 minus 1 minus 1 minus 2 epsilon squared, and you do the algebra here, and you see that this is a bound of 2 square root epsilon times 1 minus epsilon. Okay, and yeah, so that completes that's 3 way I want to say on the proofs of distinguishing quantum states. Okay, so you see that there is a very interesting relationship between how much you can distinguish your quantum state and how close your 2 quantum states are to each other. Okay, and yeah, and if you are interested in this topic, you can read more on chapter 9 about all the information theory and the distance measure between quantum states. Okay, and I think it's a good time to start now. And for the next class, we are going to talk about a bit more about quantum query complexity and how to use our Grover search algorithm to get the quantum query complexity of all different problems. Okay, and I think that's a different topic, so let's stop early today. No, so take a break early, and let's come back in 10 minutes to finish the next part of this slides. Okay, so yeah, let's take a break. Oh, okay, right. Okay, hello. get back started. Okay, and yeah, sorry for the confusion on this proof 2. I think I sorted it out. And I should also erase this thing. Okay, and yeah, so this is indeed a proof, but it's a bit hand wavy here. Okay, so we need to say that this is indeed the best way to do two outcome measurement. And so let's say suppose this the best way to do measurement is projector P prime, and then because it's the best way to do measurement, then we know that and yeah, so we actually need to say what's base. And by base we mean that its area is less than any the area is less than the area of other measurement. That means that at least the symmetric part. Okay, so we think that before we had a measurement that says P if your input is A, then you get outcome P probably is less than epsilon. Then because P prime is a better measurement, then this probability is less than P this PA. And also because before we say P on B non square is greater or equal to 1 minus epsilon, and P prime is better than B, it means that P prime is better than P, means that P prime B non square is greater or equal to P B square. Okay. And yeah, so if you just string those inequality together, then you see that you have that P prime A non square is also less than epsilon, and the P prime B non square is also greater than 1 minus epsilon. And yeah, and you should be able to do this analysis. Okay, so just a small detail. Sorry for the confusion. Okay, and so that sums up our lower bound for the quantum search problem. And yeah, and let's try to make just that sentence I say a little better. Okay, so I will keep saying we are doing the quantum search problem. And easier way to say this is saying we are calculating the OR function. And this is just really the changeable notation. Okay, because remember we said before that we said before that we can always think about correspondence between a binary function on big N input. Okay, and then we can think about the truth table of this function as just a big N big string. Okay, so before we have a small f of x from actually we have 0 to big N minus 1, but it's the same. Okay. And yeah, I guess I still change it here. Okay, yeah, never mind. Yeah, and yeah, so we have a small f. So we used to have f being like some 0 1 small n to 0 1. Okay, and we just think big N equal to a small n. And anyway. Yeah, anyway, small f is some function. It has a big N different input, and it can have this big N different truth value. And we just think about this small f input, we can just write as this big N bit string. Okay, and where okay, I guess yeah, it's this way. And so we can think about this big N bit string. We just write this big N bit string as some string x, and so the ith bit of x will just equal to f of I, the ith value of your f. Okay, and yeah, so instead of writing this small f and with as a function, we can just write a big N bit string x. Okay, and with each bit being xi. Okay, and now I think about the problem we can do on the oracle problem we can do on this big string x. There are several different ones. Okay, and the third problem we are doing is we are trying to find whether there is I in this big string x such that xi equal to 1. Okay, and you compute this thing, then you think about a logical way to compute this is you try to OR together every bit of your x. Okay, so you have x1 or x2 or 2xn. Okay, so this OR of x will equal to 1 if there is any 1, right? Because or when there is any one of the or because the OR function output 1 when any input is 1. Okay, and then if and when all those numbers, all those bits are 0, you OR them together, it will become 0. Okay, so only when all those bits are 0, this OR of x equal to 0, and when any of them equal to 1, then because you know OR between 0 and 1 is still 1, and that 1 just keep propagating, and you will get the output equal to 1. Okay, and yeah, so we found out that the Grover search, the search problem on the on this small f function can be think of as calculating the OR function on this big and big input string x. Okay, and yeah, so just some nomenclature. Then we'll think. Then the query complexity we are getting is we are getting upper bound and the lower bound the query complexity, quantum query complexity of this OR function. And the upper bound we get is upper bound of query complexity is in what way you can calculate this OR function with not so many query, and that's our Grover's algorithm. Grover algorithm shows that you can calculate this OR function with only order square root queries. And then the last thing we talked about before was lower bound on the quantum query complexity of the OR function, because we showed that to compute this OR function, we need at least square root okay, we need at least omega square root queries. Okay, and yeah, so once again, the lower bound is not a lower bound on Grover's algorithm. Grover's algorithm is upper bound, and the lower bound is really lower bound on this OR problem. OR problem is also a search problem. Okay, and yeah, and we found out because we have matching upper bound and lower bound, we totally determine the query complexity, quantum query complexity of OR function, and there is a theta square root, I should say quantum. Okay, and we also see that if we restrict our input, if we have some promise on our input, so we restrict n to either 0 or 1. So or you can write this norm of your x, that's Hemingway of x, meaning the number of ones in this x. You restrict this to 0 or 1, then we also have a query complexity theta square root n, because restrict n is actually easier for the upper bound, so upper bound is still square root n. And for the lower bound, we only say we want to distinguish between, okay, so let's go to the very beginning. So for the lower bound, we say we want to distinguish between the input that's an all-zero string or the input that has a 1 somewhere. Okay. Okay, so we found out that even if we just restrict the input to just having a 1 somewhere, you having a unique bound item is still very hard to distinguish. Okay. And yeah, so this slightly restricted problem is still pretty hard. It still requires square root queries to do. Okay, and okay, so that's about the query complexity of OR function. And with this notation, we found out that we can start the query complexity of our function. Okay, and yeah, for example, we have shown some upper bound. I guess easier one. So for example, we can also calculate the query complexity of the end function. Okay, so end function is asking whether there is a 0 somewhere in this string or everything is 1 here. Okay, if we will try to compute the end of this string, then it's x1 and x2 all the way to nxn. Then it's basically the OR function flipped around, and so it's easy to see that the query complexity of end function is also theta square root, because basically you just flip 0 and 1 and do Grover's algorithm. Okay, and the lower bound is also you flip 0 and 1. Okay, and and yeah, and there are functions that has no quantum speed up. Okay, And for example, there is this parity function. That is, you try to calculate the parity of your string. So you want to see whether number 1 in this string is an odd number or even number. If it's an even number, then you have this x1, x4, x2, all the way to xn. Okay, so if it is an odd number, then all those x all together will give you 1. Okay, and yeah, so so parity basically asks whether n is big N is an even number or odd number. So if n is odd, then parity give you 1, and n is even, then parity is 0. Okay, and then it turns out it's pretty hard to design a quantum query algorithm for this thing. Okay, this thing is even if you use a quantum query, you need theta and queries. Okay, and this is equal to, well, the randomized classical query complexity for randomized query complexity. I see. Randomized query complexity over the parity function. Or parity function, which is you basically look through everything. Okay. Yeah, so parity is a pretty hard function to compute because you basically need to look through every bit. Okay. And I guess to confuse you a little bit, there is something very similar to parity we computed before. That's the Dirichlet's algorithm. Okay, so in Dirichlet's problem, we say we want to we have our f that's 2-bit input. So our f has 2-bit input, and so x equal to x1, x2. Okay. So in our so it's very hard to spell Dirichlet. Hopefully I didn't spell this wrong. So Dirichlet's problem, we have x is just 2-bit, and we ask whether it's a balance function or we ask whether this is a balance function or a constant function. That's Dirichlet Josa, but in terms of Dirichlet, we ask whether f of x1 equal to f of x2. Okay, and so we are basically asking whether x1 plus x2 equal to 0 or 1. Okay, so that was Dirichlet's problem, and we show that this can be done in one query. Okay, in one quantum query, and of course that's the smallest you can get. Okay, yeah, Dirichlet's problem, you have this, and they use only one query. Okay, and so that's some problem and later query complexities. And now let's try to build some algorithms out of Grover's algorithm. Okay, and the first one is this speeding on the NP complete problem. And I think we already talked about this before, so let's just go through really quickly. So basically for NP complete problem, for NP complete problem, there is always a function that you can check. A function that for any NP problem, there is efficient verification of your input. So you can always check whether your input is 1 by checking some witness and with some very fast function. And by Grover search, you can just search over number of witness very quickly. Okay, and you can get a square root speed up over this brute force search over any weakness. Okay, and so you can get this square root 2 to n. Here square root 2 to n because we are talking about Boolean formula. Okay, and but as we said before, this square root in the brute force search doesn't necessarily give a speed up over basic classical algorithm. So for example, for traveling sales problem, there are these n factorial possible assignments, and the classical algorithm can actually do order 2 to the n. And basic quantum algorithm, so And so if you just use Grover search here, you get n to the 2 over n, and that's actually worse than this. And n to the 2 over n is square root n to it's a square root n to the n, and it's worse than the base classical algorithm of order 2 to the n. And so you need to do this thing smarter, and you can get the quantum speed up of is 1.728 to the n. Okay, and yeah, so here is some reference you can look up to. Okay, to how you get this quantum algorithm. Basically, you need to do Grover algorithm smarter to find out to apply Grover's algorithm smarter such that you get speed up over the classical algorithm. Okay, and then we talk about and then at the end of the class today we try to talk about some algorithms you can construct from Grover's algorithm. Okay, and the first one is this pretty. I think it's a pretty direct construction that is you try to compute n of order of n's. Okay, so this is a problem that's pretty artificial to show you how you can compose Grover's algorithm with other things. Okay, and so the idea is kind of that Grover's algorithm solves the order function. Then how about we solve a function that's so Grover's algorithm solves the order function and also solves the end function. So how about we just compose order function and end function together and see how we can apply Grover's algorithm on it. Okay? And so this order of end function we can kind of picture it in this way. So we think about once again we think about input as a big N bit input string. Okay. And we write this big N input string into the square. So we kind of assume this big N is a square number. So we can write it as a square root n times square root n grid. Okay, and so we put our input string here, and then we ask what about let's see, and we ask whether there is a row with all ones. Okay. So we are trying to, So we are trying to take end between each row. Okay. So we are trying to calculate end on each row, and then we calculate end on each row, and we calculate OR between the OR on the result of those end. Okay. And so by the example here, you see that we calculate end of each row, then we're trying to find a row that's all one. So unless it's all one, the end result is 0. Okay, so the end result is 0, 0, 0, and it's 1 here and 0, 0 here. And then this function calculates the OR on the output of those end, and then you see there's a 1 here, so the result is 1. Okay, so the result on this picture is 1. Because there is a row that's all ones. Okay, and to calculate this order of n's, then it's pretty easy to see that classically you need omega n queries. So basically you need to look through everything. Just like in the search problem, you need to look through in the usual order function, you need to look through everything. Okay, and quantally, then you think about how you can use Grover search to speed this up. And very, I guess, very natural algorithm is you just Grover search on each row. Okay, so Grover on each row you want to do end function, and we said before you can just use Grover search to do end function, and so you do Grover search on each row, and then you just see the result and calculate the order of it. Okay. So Grover search on each row, then the time you need to do on each row is n to the 1/4, because it's square root of the number of items here, which is square root n. Okay, so each end function you need n to the 1/4 time. Okay, and then the total time is square root n times this n to the 1/4, and you need actually another log factor because you want the error on each row to be pretty small. Before we have that, when we do Grover's algorithm, we only get the constant error, right? If you when we talk about Grover's algorithm, we only say how to get constant error. And it turns out if you want the 1 over n error, you want smaller error, you want 1 over n error, then you need to put the extra log n factor. And we want the 1 over n error here because there are n items here, and we want to make basically constant error over them. Then you need each 1 over n error to be just 1 over n. Okay. So you want So you want 1 over n error on each row. 1 over n error each row, and it turns out that you need extra log factor here, and so that's a bit on error, but actually, so everything together you need about n to the 3 over 4 time, 3 over 4 queries to do this. Okay, and but you think this is a bit worse than Grover's algorithm because you think. Because we know Grover's algorithm only need a square root n, and this OR function and this OR of n function kind of look like OR function. You think whether you can get the actual square root n query complexity, and indeed you can. We can do this recursive Grover's algorithm. Okay, so before we need we will be slow because. When we do this OR function, we do it classically. We just calculate each one separately and calculate the OR of the results. And actually, you can do Grover's algorithm recursively. So the OR part of this function, you also done with Grover's algorithm. So basically, you have this recursive Grover search. So you have outer Grover search that search through rows and try to calculate OR between them. Okay. And then you have inner Grover. Okay, so now the things are getting pretty interesting. Is you have inner Grover. You have inner Grover search that calculates this end function, and you think you use this a row is marked, and you use this resolve inner Grover search, or sorry, this whole inner Grover search sub-algorithm. You think this as an oracle. Okay, so you think this whole Grover search, you can think about it's a quantum algorithm, and you can always view a quantum algorithm as an oracle, right? So you have some quantum algorithm. Okay, so this is inner Grover search. You think it as a quantum algorithm, and you just look at this quantum algorithm as an oracle, and this oracle give you 1 if the result of the n is 1, and this oracle give you 0 if the result of n is 0. Okay, and so the idea is that you can always view some part of your algorithm, some sub-algorithm as a quantum oracle, and then you can do more quantum algorithm on the result of your smaller algorithm. Okay. And so you have this inner Grover and as inner Grover, and have its result as an oracle to the outer Grover. Okay. And so as we say here, so it's this thing. We treat the Grover iteration, Grover algorithm, compute the end of S0 as an oracle. Okay, so this oracle, it takes the input. The input is actually the row index. So it takes the input as an index to the row number. Okay, and you compute the end of it and end of the whole row, and store the result on the face here. Okay, so of I equal to -1 to the end of ith row, and on this I. Okay. Okay, and with this, then we can think about the total time complexity of this algorithm is the is the query complexity of the auto algorithm that's square root n, because there are n items in square root, and then times the and so that's how many. So this is how many inner oracle call. How many oracle call this outer algorithm need to do, and each oracle call is actually done by the inner Grover. And inner Grover need square root n, as we said before, and then there's also this log factor we need to do as before. We need to have the inner Grover to be pretty accurate. Okay, and so the end result is that you need square root and log n queries to do this. Okay, any question? So this shows us how you string Grover's algorithm together. You can recursively call each other by viewing the result of some Grover algorithm as oracle to other functions or other bigger algorithms. Okay, and if not, then we can do this even more. Okay, so now this is just the order of n's, and we can think about we can build this higher. So what if we have an and or tree, and so we can have or function on several result of and on several end function, and these end function are on result of several or function, etc. So we have a tree that's that's or and or and or and in the very bottom we have some inputs here. Okay, you can think about function that have this tree structure. Okay, so at the very bottom, then you have your x1, x2, da da da, maybe x begin, feed to some and or. Okay, so you can think about this and or tree function. Okay, and you now things are actually getting a lot more useful. So before we said this or of end function, we think this is pretty artificial function. We think about okay, so maybe some theorists just want to compose or function and end function, and yeah, why we want to calculate this. And but it turns out this and or tree function, at the main level, is something that I guess you don't really compute every day, but it's very useful because it corresponds to gain tree of many gains. Okay, so it's a gain tree for gains like chase or go. Okay, so actually any two-pair turn-based gain can be turned into an or tree. Okay, and I guess we can think about how how this goes is that we are trying to compute whether whether this game can be won by player 1 or player 2. Okay, so we think about we have some the chess game or the go game. So chess is like 西洋棋 and the go is 围棋. Okay, and anyway, so any kind of those game, we can compute whether a given situation is a win or lose for the player going to play. Okay, and so the tree basically goes like this. It says that so the or basically means the turn for me. Okay, so there are two players. So player 1 is me, and player 2 is the other player. Okay, and then what you can do is there are several moves I can do, and whether I can win or not depends on whether any move I can make me win. Okay, so those branches of or is the moves I can make, and I want to calculate the or between those branches because I want to see whether there's any winning move I can make. And then the end is the other player. The other player will also want to win, and so the other player will search for all the moves he can make, and pick a move that make me lose. Okay, and so there's a tree between what I can do and what the other player can do, and the end result are the configuration where either I win or I lose. Okay, and I win is 1 and I lose is 0. Okay. And so you see that if we can calculate the result of n tree really quickly, then we can solve actually a lot of games. Okay, so all those two-player turn-based games like chess or Go can be done by search through a huge NO tree. But obviously this is not totally practical. But in theory, you can solve a game like in this way. So. But in practice, usually there are a lot of moves you can make on each branching, so the search space of this thing will be huge. But nonetheless, this will be this is a theoretical way to search any two-player turn-based game. Okay, and that's about why this NO tree is useful. But now go back to quantum kernel complexity and. Now we have this NO tree, and we think about maybe Grover's algorithm can help us speed up search through this NO tree. So we have this huge input string, and then we want to solve the result of this NO tree. Okay, and then you think, okay, so this NO tree is just this and all of n are more levels, and so you can just recursive your Grover's many levels. And solve this NO tree, and turns out that actually doesn't work. Okay, so this is a bit funny. Okay, so the recursion actually doesn't work here. You just use Grover's algorithm on each layer. That don't give you a square root speed up because the tree might possibly has many labels. Okay, and yeah, so because there are many labels, you need to have your error very small at the bottom level. And so if you calculate the error very carefully, so this log n factor, if there are many layers, then the error you need is too small at the bottom level. That means the Grover search algorithm not efficient enough to solve this NO tree. Okay, and yeah. Where do I? Okay, yeah. So recursion don't solve the NO tree, but actually it turns out there is still a square root algorithm, and it's by quantum walk. Actually continuous and quantum walk, and it's an interesting paper, and you can look up here. Yeah, so it's a quantum algorithm for this NAND tree. And I guess it will be a bit hard to read this paper, but it's quite interesting because you use some physics idea to solve this NO tree problem. Okay, and yeah, so that's NO tree. I guess it's not quite Grover's application of Grover's algorithm, but it's not quite the regular application of Grover's algorithm, but the existence of Grover's algorithm does inspire people to look for order square root and quantum algorithm for this problem. Okay, and now we talk about more direct application of Grover's algorithm is this collision problem. Okay, and okay, so we are very short on time. Yeah, so this collision problem, this is kind of similar to what we had before. So remember we have the Simmons problem, but this is a bit different. So this is like Simmons problem, but less structure. So we're trying to find a collision given Blake's sparse function. Okay. Yeah, I guess I back to this function description instead of B-string description of our input. Okay. So we have the input Blake's sparse access to this function, and it's not Boolean anymore. It's an big N input function to big N output function. Okay. And let's assume this big N is even. And so it's promised that your f is either 1 to 1, so every input mapped to a unique output, or 2 to 1, meaning that there is some input make to, so every 2 input will make to the same output. Okay, so 2 to 1 means that it's a lot of collision, and by collision means that. So once again, collision means that some x and y different from each other, so x not equal to y, such that f of x equal to f of y. Okay, this is a collision. So this is what we mean by collision. this collision. And yeah, so we have seen this before in Simon's algorithm, where we want to find two different inputs to this small f, such that they have the same output. So f of x equal to f of y. Okay. And anyway, so our problem is a promise problem. So our promise that f is either 1 to 1, such that for all x, f of x are different, or is a 2 to 1 function. So for all x, there is some y such that f of x equal to f of y. And our problem is simpler to decide whether f is 1 to 1 or 2 to 1. And classically, this can be done in theta square root n time. And use the birthday attack. Basically, you pick so basically any random pair has theta 1 over square has a 1/1 probability to be a collision. Then if you just pick a square root element, then they are order n pairs, so there will be pretty good probability to find a collision in these pairs. Okay, so that's classical. And quantally, then we want to use Grover search algorithm to speed up finding a collision here. And then we start doing smarter function, smarter construction. Okay, so we have a pretty smart construction to do this using order square root n queries. Okay, and let's see. Okay, and the query complexity, the algorithm is in this way. I think we're short on time, so this probably be the last algorithm we talk about. Okay, and the algorithm first query. Sorry, there are two algorithms. Okay, and sorry for confusion. So the first algorithm uses order square root n query, and the second algorithm is better use order n to the 1/3 query. And let's see the dumb algorithm can do. Okay, so the easy algorithm is you just query f of 1, and you go research for so you know what's f of 1, and then you just search go research for items such that f of x equal to f of y. You try to find a collision this way. Okay? And this needs order square root n queries because you need to search over n items. Okay, there are n items that are not equal to 1. You need to, and there is only one of them. Collision is 1. Okay, so this need order square root n queries, and that's same as classical query complexity. And so we are happy about this because we think there should be some quantum speed up on this question. And then we figure that that's because classically we are doing this smarter. We are not just finding a specific pair. In this algorithm, we want to find a specific pair to this f of 1. Okay. But classically, we are able to find many items, and we want to check whether any one of them has a pair, has a collision between. So we pick square root n items, and there are order n pairs that we can check through. Okay. And how do we try to replicate that with the quantum algorithm? Is we kind of do this in a funny way. We do it also in a two-step process. Okay, so first we just so the quantum algorithm we do is first we pick n to the 1/3 item, and then we just look through all of them. Okay, so we query them classically basically, and then we write down all the results. Okay, so there is this. So there are going to be two sets. There is S1 with n to the 1/3 item, and there is set S2 with n to the 2/3 item. Okay, and S1 we just look through everything, and so we know what everything inside S1 be. Okay, what everything inside S1 is. Okay, I guess this S1 is look through. Okay, so this is we're going a bit fast. So this S1 is a subset of the input. So S1 is a subset of so S1 is a subset of this bigger input. Okay, and so basically look through f of S1. So we look through what's the output of everything inside S1. Okay, so we record every output, every possible output for things inside S1. Okay, and then we pick another S2. Okay, and so this S2 we don't actually query it yet. Okay, So we just pick randomly pick this n to the 3 over 2, 2 over 3 items, okay? And we don't query them, but we Grover search over it, okay? We Grover search over this item, okay? And then this Grover search, we need to decide some oracle to search, right? So we have a very complicated oracle to search. This oracle is marked. Okay, so we have a very complicated oracle here. So the oracle has the input being the item inside S2. Okay, so the oracle has the item being input being items inside S2, and the item is marked by doing a pretty complicated algorithm. By algorithm that use the information recorded down on S1. Okay, so the item is marked if there is x inside S1 such that f of x equal to 1. Okay, this is something we can do because we already write down everything inside S1. Okay, and so actually each of these oracle code. This is a very complicated oracle code. So this oracle with input inside S2 and mark if there is x inside S1 such that f of x equal to x fy. This oracle code can be done by only one query. So you only need to, so if you want to query some y, you only need to doing one query on y. So to calculate f of y. Okay. So only need to use one query to determine whether y is marked for all y, because you already write down all f of x. Okay, so f of x is already queried, and you write down them classically, so it can be reused into when you construct this oracle. When you construct this oracle for your Grover search. Okay, and so each oracle code. Each oracle of this Grover search can be done by a query to your f, by one query to your f. So the number of query to do this Grover search is square root of number of items to search over is square root n over n to the 2/3. And so the total number of query of this algorithm is n to the 1/3 to look through everything S1. And square root of n to the 2/3 to Grover search over S2, and so its total number of query is n to the 1/3. Okay, and okay, so this is the number of query order 1 n to the 1/3 as I said before, and then also count number of pairs that we search through, just like in this birthday attack. So the number of pairs of input we search through is n to the 1/3 times n to the 2/3, and is order n. Okay, and so there is a constant probability you can find. So once again, there is order n pairs you look through, and just like the argument of birthday attack we had before. Argument of birthday attack we had before. So actually, we have a constant probability to find a collision. Okay, and so we see that we can actually use order n to the 1/3 query to find the collision. Order n to the 1/3 quantum query to find the collision inside this function. Okay, and also this is for query complexity, and if done with some smart data structure, then it can be done in time order n to the 1/3, and then you can prove that this order 1 n to the 1/3 query complexity is tight, because you can give a query lower bound of omega n to the 1/3, and the lower bound is done in this algorithm. Okay, and so that's the collision problem. And so I guess we have 5 minutes left, so we don't have time to go through the next algorithm, but it's fun to see through different problems. Okay, and so there's this collision problem that's trying to find a collision try to determine whether it's a collision with its pretty strong promise, where if it's 1 to 1 or 2 to 1, And we can also kind of do this problem without promise, and that's the element distinction problem. So we still have the similar input. F is B. F has an input of size n to the output of size n, and there's no promise on what F looks like. And the problem is determine whether F is 1 to 1, and so determine whether every input gives a different output, or there is some input that gives the same output. Okay, and for example, we have n equal to 4, and say this function is 1 mapped to 1, 2 mapped to 2, and 3 mapped to 3, and 4 mapped to 1 together again, and then we see there is a collision. And just intuitively, element distinctness is harder than collision because there are just less collision to be found. So in the worst case, as we see here, there can be just one collision out of this n input. Okay, so maybe everything is different, but just two of them is a collision. And just because the number of collision is lower, it's harder to find them. Okay, because there are actually n pairs of collision. Okay, so we have a lot, so there is actually n over 2 pairs of collision here. Because when there is a collision, then everything is a pair, is a collide to other thing. Okay, as compared to this element distinctness, where there can be only one collision. So this is harder, and classically you can see this is harder because you can no longer do birthday paradox, and you just need to look through everything to find whether there is a collision. So you need theta and query. Okay, and quantally we'll skip over the algorithm. So you can use once again you can use recursive Grover's algorithm to do n to the 3 over 4 to construct n to the 3 over 4 algorithm. And but it's not optimal. You want the optimal algorithm, then you need to do discrete time quantum work, and then you can get to a 2/3 algorithm, and that's optimal. Okay, yeah, and so if you want the reference is in this famous paper of quantum algorithm for element distinctness, quantum work algorithm for element distinctness. And then finally we have easier problem to do, and yeah. And you can also use Grover search algorithm to do this minimum finding algorithm. And this is actually, I would say, it's a pretty useful algorithm because you can use it to construct algorithm. So minimum finding is this problem where this is a pretty interesting output. Okay. So it is a problem where once again you have an input and they are mapped to just a real number, and you want to find the input you want to find something inside this input to give you the minimum number, the minimum output. Okay, so you can think about, you can feel that this is a pretty generic thing. You want to find the minimum output over several inputs. Okay. Minimum value over several values. Okay, and indeed this can also be done in order square root time by Grover search algorithm, and it's pretty easy. So this is this can be done in a homework problem that may or may not be actually in a homework. And yeah, and you can prove that this square root time is optimal by having a reduction to a search problem. So I think the lower bound is actually easier than upper bound. So you can pretty easy to construct a function such that solving a minimum finding will solve the search problem, so that you see the lower bound of a search problem will become a lower bound for minimum finding. Okay. And I think that's about time. The next slide we have some complexity class that we actually talked before. So we have BQP, that's bounded the problem that can be solved by basically efficiently by quantum algorithms of bounded quantum polynomial time, and then we have the P space, that's a problem solved by polynomial space, and then there's a QMA problem, that's kind of the quantum version of NP, where it's a problem that can be efficiently verified by quantum computer, also using a quantum witness. And we have everything here, the non-complexity class here. So we see everything is actually inside P space, and we have a P, and then we have an NP problem, and we don't know what's the relationship between BQP and NP. We think, maybe something in NP is not solved by BQP, and something BQP is not solved by NP. We don't really know. And there is a QMA that's larger than BQP and NP, and the P space contains everything. Okay, and I think that'll be the last slide. And so next week we are going to be, I think we are going to talk, I haven't totally decided yet, but we are going to talk something pretty casual. So I think on Tuesday we'll teach you about how to use Qiskit, and on Thursday we'll probably do the final review. Okay. And if I found something else extra interesting, then maybe we'll actually talk a little more on Thursday too. Okay. And so I'll see you on next Tuesday. And that'll be end of class today.